What we're going to look at in this next video is we're now going to take our intermolecular forces and talk about how this shows up in different properties of our molecules. So we've already talked about boiling point some. That'll come back up, but we're going to talk about a few others. So the first one we're going to talk about is the concept of surface tension. So I'd like an example first instead of trying to use the technical definition of this. So if we take a penny, my very large penny, and we put water drops on top of it, what will happen initially is you'll get a dome shape. And so that dome will be filled with water. I was going to try to fill it in, but that doesn't look very much like water, but it should be blue, but you get the idea. And as you add drops, eventually the dome that forms is going to get too big and it's going to fall off the penny. If you do this with other liquids that have weaker intermolecular forces, it's either not going to form a dome at all, or it's not going to get a very big dome, and it's going to fall apart. So the question is, why is that? What causes that dome to form? It's related to a concept called surface tension. So what's happening here is if you've got a substance, so we've got a bunch of molecules in that substance, and let's assume these are equally spaced out because let's pretend I can draw better than I actually can, and then it's going to keep going. What's important is notice if you look at a molecule in the middle, it can interact with up to 6 other molecules close by. But if you take one at the edge, it's going to have fewer interactions. I believe it's an average of 4. And it depends on the exact shape of this molecule and how it goes. But the important thing is those edges have fewer interactions. That means as your intermolecular forces increase in strength, the molecules less and less want to be on the edge. That being on the edge is a negative because it can't interact with the other molecules. Now, there's some interaction from this that helps make this stabilize so we can get this dome shape. But we also know that domes of liquids don't form naturally like that. They would normally just roll off the penny because of gravity. So surface tension is going to be the energy related to this. And specifically, I'm going to go with surface tension as a property of liquids that results from the tendency of liquids to minimize their surface area. So that's a technical sounding way to say it comes from trying to minimize these, or to maximize how many intermolecular forces it has. So it's trying to minimize surface area with its shape. Eventually, gravity takes over and will squish it down so that it doesn't form this dome. So what that means is as our intermolecular forces, our IMF, increase, what that leads to is an increase in the force that allows for surface tension. So if we were able to increase intermolecular forces more, take something other than water that actually has stronger intermolecular forces, we could make a bigger dome. It has a higher energy that it's able to overcome of gravity. It's able to better form this. On the other hand, if you take something like an oil, for example, that only has dispersion forces, if those dispersion forces are weaker than the hydrogen bonding in water, it's not going to form a dome as easily. It's going to break a lot sooner because it doesn't have as strong a surface tension. So that is property 1. So we're just going to go over a list of properties right now. So next is viscosity. So this is related to how easy it is to pour something. Specifically, the way we word it is resistance, I can spell, really I can, to liquid flow. So substances that are really thick, if I try to pour them, like if we got a little graduated cylinder here that I measured something in and there's a liquid in it that's trying to come out and I'm trying to pour it into a beaker here, pouring, it's going to pour really fast if there aren't very many intermolecular forces because it's easy to get it through. Because it's not going to resist as much. But if I've got low intermolecular forces, if I've got high intermolecular forces, it's going to be cohesive, it's going to connect to itself, it's not going to want to pour as easily. Now, so we can increase the viscosity of something, means it's going to have a stronger resistance to flow because the molecules like each other more and don't want to move away from themselves. So what that means is as we increase our intermolecular forces, that leads to an increase in viscosity. And if you're reading along with your text, it access to numerical measurements of this and something called centipose. That's what CP stands for there. I'll just mention I'm not going to ask you to do this in a particular unit. We're not trying to numerically calculate viscosity in this class. I just want to mention it so that there's not some term somewhere that makes you go, oh, wait, that doesn't sound like anything I've ever heard of. That's just some letters. So that's what that is. It's just a numeric way of measuring viscosity. So if we increase intermolecular forces, we increase the viscosity. The other thing we can do related to viscosity is if we increase the temperature, we get something that is less viscous. That's because since the molecules have more energy, it's easier to overcome those intermolecular forces and continue to flow because it's got more energy into it, which also means the reverse is true. If you decrease the temperature while remaining liquid, it's going to increase the viscosity. And this is something you may have an intuitive feel for if you have something like a thick pancake syrup, but you have one of those that goes in the microwave when you heat it up. When you heat that one up, it'll become thinner. It's easier to get it out of the bottle quickly because it's less viscous. As you've increased the temperature, the molecules are able to move around more rapidly and they can get around each other more easily that way. So that was the second property we were going to discuss. The third one is something we call capillary action. So capillary action is going to be the ability of a liquid to flow up a thin tube against the force of gravity. So we've got a tube, and we have it in a dish that's got some water in it. Let's say, so this has water. I didn't draw a very good dish. But what's going to happen is some of the water is going to stick to the sides of this tube. The reason it's going to stick to the sides is because it's going to have adhesive forces where it goes, oh, this water really likes this glass tube, and it's going to pull itself up a little bit so it can touch the glass tube more. Well, when it does that, if we keep going, what's going to happen is the other water is going to join it because it's going to want to stay together because it's like, no, we like other water molecules. We have lots of intermolecular actions, so it's going to pull it up, and it's going to match up with the level that it got attached to. Then the water is going to start trying to creep up more and more. It's going to keep trying to creep along to the sides. Like, no, I want to get pulled up more. Eventually, you get to the point where it looks like this because it's gone up far enough that gravity is now strong enough to keep it from still attaching more. Because eventually it can't just go forever. It realizes, oh, I'm above the water line above everything else. I'd like to go down because of gravity, but I want to go up because of capillary action, and it ties itself up where it's exactly the forces are balanced. So what's causing this to happen is that you have adhesive forces. Those are the ones that cause the water molecules to stick to the glass because it likes it. You also have cohesive forces. These are the ones where the water molecules want to stick together, and that's what pulls up the middle molecules that aren't directly touching the glass. And it travels up as much as it can. This is something you may have seen before, for example, with, with celery. I've seen lots of videos on YouTube or students doing it in like middle school classrooms, maybe elementary, I don't remember. Because initially it's just cool. It's like, oh, the celery changes color because I put a colored liquid water and it travels up. And the idea is you've got lots of xylem in your celery, and that's able to have the water come up due to these adhesive and cohesive forces. So it pulls it up, and you can see that happen. And in the case of plants, then the water will actually evaporate at the ends, and that will allow more water to travel through, and so it can keep traveling up that way, using capillary action to help it get up there. This also means that this process of getting it to travel up the tube will depend on the material the tube's made of. So we're basically going to just do this in class with glass. But if you try to do a metal tube, for example, it's not going to interact the same way. It's not going to travel up like that. And the other thing to point out is because at the very end, a little bit is stuck to the side, but the cohesive forces aren't enough to pull it up, that's why you get a meniscus. So remember when you're reading, we taught you in 1211 when you're reading, you have to read along the meniscus. So we have to read along this bottom level here. That dotted line should touch the thing I'm not good at drawing on this tablet really accurately. So the dotted line should touch right at the bottom of that, and that's what you're reading because the glass is the way it's calibrated is assuming that the way the adhesive forces work, you're reading the bottom of it instead. So it's related to it trying to pull up a little bit on the sides. Now, our graduated cylinder is so large, you're not going to see a significant effect of capillary action. It's not going to let it travel up an extra 10 milliliters or something if you've got a bunch of water at the bottom. But when you get really tiny tubes, you're able to see a lot of travel up because since it's the tinier tube, it's able to pull it up further. So that gets us our capillary action. So the last one to mention is going to be related to our boiling point. It's going to be related to the process of vaporization. So what happens in vaporization is that molecules are able to go from the liquid to the gas form. So I've got a beaker, and we've got lots of molecules inside here. And once a molecule reaches the surface, if it has enough energy, it's able to escape. Can escape with enough energy. So the question is, what makes something have enough energy, and why is it that some molecules can escape and others can't? So first, let's go back to this idea of temperature distribution, or heat distribution. So if you have a substance at a particular temperature, the temperature is related to the average energy of those molecules. But so this is our energy and our number of molecules. Now what's important is when you talk about an average, is some of the molecules are going to be down here, and they're going to be really, really slow comparatively. They don't have as much energy. And some molecules are going to be up here. Towards the right side, they're going to have lots of energy. And so for any substance, there's some point where they're able to escape. So this is going to be energy required for escape, let's say. And it's different for different molecules where it'll be placed. So what happens is each time a molecule reaches the surface, because it's randomly moving around inside our beaker, if it's got enough energy when it gets to the top, it'll boop, pop out of the liquid and become a gas. Now, that makes sense that some molecules that have enough energy could escape, but how is that related to intermolecular forces? So as you increase the intermolecular forces that your molecule is feeling, it becomes a higher amount of energy to escape. That means it's not going to vaporize as easily. This is because, since the molecules like each other more because they've got more interactions, when they escape into the air, remember we said air molecules are super spread out once they get the gas form. Because they're all spread out, they're not going to interact as much, which means now they don't have those intermolecular forces for the most part, or if you're treating them as an ideal gas at all. So because of that, when they escape, they don't have their friends anymore. So you have to have enough energy that the molecule doesn't care about that. It's like, no, I got so much energy I want to keep moving that even all my friends can't hold me back here. That my intermolecular forces keep me there. So that's going to happen to that. So making sure real quick I didn't miss something. Oh, right. There's a piece of terminology that gets used sometimes that just our text uses it, and I want to make sure you know it. Volatile means easy to escape, basically. Easy to vaporize. So a substance that is volatile will easily turn into a vapor, while there's something that is non-volatile will not readily vaporize. So it's not going to escape very easily. So some substances, if you put them out at room temperature, really easily turn into gas. And some don't. And I'm going to disappear my head. There we go. I covered that up. So if you think about it, if you have a dish of water and you leave it out, eventually it will all evaporate. Now it may take a while depending on the temperature outside and how much humidity there is. So it won't all escape right away, but eventually it'll all evaporate. But we said that boiling requires 100 degrees Celsius. That's only true for all of it to try to escape This is why the water molecules can over time get away. Because even though they're not at 100 degrees Celsius, some of the molecules have enough energy, when they reach the top, they can escape. Another important point about this, so we'll go to a new slide, is that when the molecules escape, so the ones that escape, the escaping ones, have the most energy of all of the molecules that are in the water. So what that means is for the remaining water, when a water molecule leaves, there is now less energy in the water because our faster molecule was the one that got out. So it got rid of the highest energy molecules, leaving just the medium and low energy molecules remaining. So this is a way to remove energy from the liquid water, and so it gets gained by the water, by what's coming into the gas. It's going to be higher. The reverse can also happen, which especially in, let's say, a closed container. Let's say I close my beaker off now. And now, as the water escapes, the water that escapes is up top now. So these are sometimes going to collide with the surface. And if they have a low enough energy to be captured by the water molecules on the surface, they rejoin the liquid water phase. So they can condense and reform that. So in here are lower energy for the gas. They still might be high energy compared to the ones in the liquid, but they have to be a low enough energy they can be recaptured. So the lower energy gaseous water molecules can rejoin the liquid. Now, it's important we mention this is closed. So if you go in a room and you set a cup down, water will not spontaneously fill that cup. That's because there aren't enough water molecules. There aren't going to be collisions happening. Or if I have a little bit of water, it's not suddenly going to grow. Now, if I close it off and there's a lot of water vapor inside, it might change a little bit. But what's important is when we close the container, the density of water molecules is increasing in the gas phase, so it's easier for them to rejoin. When you put it in an open room, that little glass of water doesn't significantly increase the humidity of the room. So there aren't a bunch of new water molecules that can all collide with the surface. That's why you're not going to get it to spontaneously just grow water in there. Eventually, you get to the point where the amount rejoining and leaving, at least in a closed system, matches. So what you get is eventually, as they rejoin, some leave. So eventually, the rates of vaporization, it lagged on my screen, I don't know if it did on yours. Eventually rates of vaporization and condensation match. And what that means is the same number of molecules are going to re-enter the liquid phase as go into the gas phase. This doesn't mean that individual molecules can't change phases, but you're not going to see the number of molecules change. So for each time one gets vaporized, one is going to condense. This is called dynamic equilibrium. And we're going to talk about equilibrium a lot more. We have a whole chapter on it in a few chapters. But the basic idea is that equilibrium is going to be a state where, while individual molecules may be changing their phase or their composition later, the net number of them is going to stay the same. And so eventually we get to this point and we don't see any more leaving than we do gaining. So the liquid water level is going to stay the same. Now, we have one more thing to do before we can finish this video, and that's we have to talk about this in a numeric sense. So we have something called the delta enthalpy of vaporization. This is related to amount of energy to change phases. And it'll depend on the name of the enthalpy for exactly which one to change phases. So vaporization would specifically be for liquid to gas. So the enthalpy of vaporization is how much energy I need to put into the molecule once it's at its boiling point to get it to go from liquid into gas. How much energy is that? So for example, for water, let me get my number. So for water, because we're going to work on a problem in a second, this delta H of vaporization is going to be equal to 40.7 kilojoules per mole. Now I also want to note that this is related to the delta H of condensation as well. So vaporization is liquid to gas, condensation is gas to liquid. And they're just the opposite of each other. So if it takes 40.7 kilojoules per mole to vaporize a water molecule, or a mole of them, it has to absorb, it's going to release 40.7 kilojoules of energy when a mole of them condense back down. So delta H of vaporization is always going to be positive, and delta H of condensation is always going to be negative. They're opposites of each other. So how do we do this as a problem now? So let's say we wanted to, do another stream. So we're going to, I'm just going to grab one from my note. Let me find something real quick. This will take just a moment. I'm going to grab a problem, that way I don't have to handwrite it. Let's copy this over. Okay, Discord. Okay, so let's work this one. So we want to calculate the mass of water that can be vaporized at its boiling point with 155 kilojoules of energy. So what we know, and the way we're going to represent this, is the amount of heat, Q, it takes to phase change is equal to the moles times the delta H of vaporization. Note that it is N is moles if delta H vaporization is kilojoules per mole, or like joules per mole or something. You can also do a version where you have M, which is mass, if you have a delta H reported in kilojoules per gram. So you could also, or like joules per gram or something. So it'll depend on the units of your enthalpy of vaporization, whether you're going to use moles or mass, because you have to have these things cancel each other out. When you look these up in a table, they're usually going to be in kilojoules per mole, but I've occasionally seen some things that talk about it in per gram, so I wanted to make sure you knew that so that it wasn't a surprise. I put my moles in. Why did I get the wrong answer? Well, because it was in grams instead. So this phase change is specifically already at its boiling point. In a future video, we're going to talk about how to deal with if it's not at its boiling point, how we figure this out. But so this enthalpy of vaporization is energy to change phases at the point where it's already at the temperature it needs to be at. So we know Q is 155 kilojoules, they told us. We don't know N. And we know delta H of vaporization is 40.7 kilojoules per mole. So I'm going to divide both sides by 40.7 kilojoules per mole. And when I do that, see what I get. I haven't done this one yet. I'm going to get 3.80 moles of water. Now, this isn't what the question asks. It asks for mass. So don't forget, we still have to do those 1211 ideas if they get asked. So 3.8 moles of water. We know. Make my face disappear in case I write over it. You didn't need my whole face. You needed the problem. There we go. Every mole of water is going to have a mass of 18.02 grams. So we have 3.8 times 18.02. And that's going to give us 68.5 grams of water can be vaporized using our 155 kilojoules of energy. So that finishes up this section. I just wanted to show we can also do this in a numeric form, and we'll continue to do that in the next coming chapters as well, of how to do some more math on these instead of just so far we've just covered the conceptual stuff of what we do with it.